we're going to talk about the serious problems that exist with the way the history of proofs in mathematics has been written, and reflect on all the stories that can and still need to be written by diving into ancient Sanskrit mathematical sources to look at interesting and surprising ways in which different authors reasoned on and with mathematical objects. Indeed, standard histories of proofs in mathematics often say nothing of mathematical texts outside of Europe, as if they didn't exist. And if by chance they do evoke in other languages than European ones, they evoke texts in other languages than European ones, we can encounter, for instance, the kind of statements given by Maurice Klein, a teacher and mathematics popularizer in his classic Mathematical Thoughts from Ancient to Modern Times, which was published in 1972. So he writes, perhaps most interesting is the Hindus' and Arabs' self-contradictory concept of mathematics. Both worked freely in arithmetic and algebra, and yet did not concern themselves at all with the notion of proof. That the Egyptians and Babylonians were content to accept their few arithmetic and geometric rules on an empirical basis is not surprising. This is a natural basis for almost all human knowledge. But the Hindus and Arabs were aware of the totally new concept of mathematical proof promulgated by the Greeks. Both civilizations were, on the whole, uncritical, despite the Arabic commentaries on Euclid. Hence, they may have been content to take mathematics as they found it. So, such stands are all the more surprising that, as I will show in part in what follows, all sorts of mathematical texts in Arabic, Sanskrit, but also in Chinese, containing proofs and sometimes quite elaborate reasonings, have been known and studied in Europe from the beginning of the 19th century. In other words, but you probably already know this, the history of mathematical proofs has been and continues to be a very political history. So, in what follows, my aim will be to give a display of the diversity of mathematical reasonings that can be found in Sanskrit mathematical texts, to show that as we decolonize the library from which we choose the texts with which we study mathematical reasonings, we might also question the focus we have on the notion of proof, that is, on the will to find rigorous, irrevocable reasonings dealing with the truth of a mathematical assessment. I think that we are all aware that ideas of what makes a valid reasoning in general and in mathematics in particular have undergone radical changes in the late 20th and beginning of the 21st century, and as algorithmics and statistical approaches to proofs have gained momentum. And humans in the past too actually had many different ways of reasoning in mathematics and many different ways of thinking of what made a valid reasoning. And this diversity, I think, I want to argue, is worth studying too. So exactly 10 years ago, Karin Shemla edited a book that made quite a sensation in the discipline of the history of ancient mathematics, and it's called The History of Mathematical Proof in Ancient Traditions. The studies in this book continue to inspire historians of ancient mathematics today, notably the study of mathematical diagrams and the way they have been edited. So in the introduction, Shemla first establishes what from the end of the 19th century would have been the stabilized standard history of proof, which the previous speakers actually have already talked about. But so she says that it's in the end of the 19th century that people have decided, or that most historians and mathematicians actually also would write that we owe the idea of mathematical proof to mathematicians of Greek antiquity, especially to Euclid's Elements, which itself would have been inspired by Aristotle's posterior analytics, and that central to the idea of proof would have been the idea of the certitude of the veracity of a statement, and so that the correlate would have been the importance of rigor. And in this idea was that before classical Greece, there would have been no evidence of proof. And furthermore, this unique idea of proof would later have been developed only in Europe. And in other words, this idea of proof is part of what would have made classical Greece and modern Europe exceptional. So we can amend this standard idea of the history of mathematical proof in many ways. We know from the previous speakers that such a history and such a definition should be infinitely more complex. And Shemla remarks that mathematicians of today read proofs for many reasons, not just to be convinced by the truth of or the correctness of a statement. And we can also think that this might have also been the case in the past. And she also shows that such a model of proof was used for all sorts of things that have nothing to do with mathematics, like, for instance, to be a model of rigorous reasoning for philosophers, or thought of as a tool by Jesuits for conversions to Christianism. And so, I think it's already obvious, such a definition has been then used as a landmark by which reasonings in past mathematical texts were judged. It serves until today as a criteria by which certain corpus of sources are accepted as containing proofs and others not. But truly, when we read mathematical documents of the past, some mathematical texts may adhere more or less to this standard, but many do not. So that this way of valuing text conveniently selects some text and discards other. In other words, Klein's point of view has a long story. And we can go back to the middle of the 19th century, for instance, and to see what it actually echoes into. Klein's 1972 statement sort of echoes into what Jean-Baptiste Biot said 100 years before him, who was a French mathematician, astronomer, and physicist, who wrote in 1841. The peculiar habit of mind following which the Arabs, as the Chinese and the Hindus, limited their scientific writings to the statement of a series of rules, which, once given, ought only to be verified by their applications without requiring any logical demonstration or connections between them, this gives those Oriental nations a remarkable character of dissimilarity. I would even add of intellectual inferiority comparatively to the Greeks, with whom any proposition is established by reasoning and generates logically deduced consequences. But actually, what the contributors to Shemla's book show is that during the first 3/4 of the 19th century, there were many different ideas of proofs that were discussed by mathematicians and historians of mathematics. It was possible to imagine algebraical proofs, notably, which implied not to dismiss the history of computation or algebra as secondary or of no interest for the history of mathematical proof. And so the adoption of a standard shape and history of proof took hold in the history and philosophy of mathematics at the end of the 19th century. And it led to discarding all sorts of mathematical texts, not only those in Chinese and in Sanskrit, but also those in Greek or in Latin that did not follow these norms. So it's this creation of a limited corpus of ancient texts of mathematical proofs that I call a colonial library, and in part because it was constructed at the height of the European imperial expansion. And it's the whole constitution of such a library that I think we should reconsider. So, in what follows, first I would like to underline that part of the problem in the history of mathematical proofs, which is a wider historiographical problem, is that some discourses have attached modes of reasoning to peoples, nations, or religions in a homogeneous way, and that this fuels identity politics in the history of mathematics. And second, that we can document the mathematical reasoning we find in texts, studying together the practices of reasonings they testify of, the aims of these reasonings, and the kind of texts that were shaped for this aim. This means going beyond the idea of proof, because past mathematicians have written reasonings whose aims might not have been limited to establishing the truth of a statement or the correctness of an algorithm. For example, they could aim at providing generalizations or want to show that a mathematical object or a procedure can be interpreted in different mathematical and non-mathematical contexts, for instance. So I'll first show how the history of proof was important in the writing of the history of mathematics in South Asia, and then underline the dangers of nationalist historiographies, even when they focus on actors' categories, and then provide examples of the diversity of mathematical reasonings that can be found in Sanskrit mathematical sources. So at the end of the 18th century, a Scottish mathematician and philosopher, John Playfair, officially called for a search for mathematical texts from South Asia. And one of the interesting things about his call is that he had an equal interest in geometry, arithmetic, and astronomy. And this is in contrast to the usual focus on geometry as being, the great tradition of mathematics. Henry Thomas Colebrook, who is known as the father of Indology, and who knew Playfair and read him, took an early interest in collecting manuscripts of mathematics and astronomy in Sanskrit during his long stay in India, first as a member of the East Indian Company and then as the head of the Asiatic Society of Bengal in Calcutta. And after spending more than 30 years in India, he composed the most influential and enduring translation of Sanskrit mathematical texts in English of the early 19th century, which is this book that came out in 1817 called Algebra with Arithmetic and Mensuration. So in particular, he worked on Bhaskara's two, we call him to distinguish him from another Bhaskara we're going to see, who is a younger Bhaskara 1, mathematical text devoted to arithmetic, the Lilavati, which is actually the name of the young woman to whom supposedly part of the problems are addressed, but Lilavati means also with fun. And in his algebra, Bijaganita. So his translation starts with a preliminary dissertation in which he declares that indeed Sanskrit mathematical texts contain proofs. So this is what he writes. On the subject of demonstrations, it's to be remarked that the Hindu mathematicians proved propositions both algebraically and geometrically, as is particularly noticed by Bhaskara himself toward the close of his algebra, where he gives both modes of proof of a remarkable method for the solution of indeterminate problems, which involve a factum of two unknown quantities. So he takes to claim that ancient Hindu mathematicians had both algebraical and geometrical demonstrations, he's using some of Bhaskara's statements that are in a very localized place of his algebra, in which, if I read Colebrook's translation of the text, at some point Bhaskara writes, the demonstration follows, it is twofold in every case, one geometrical and the other algebraic. And he writes a little bit later, the algebraic demonstration must be exhibited to those who do not comprehend the geometric one. And the term that Colebrook translates as demonstration from the Sanskrit is upapati, and we'll be interested in this term, you can see it here, which will become the standard term translated from the Sanskrit into English as proof. So we can come back to what Colebrook is doing here. He's actually taking some assertions made by Bhaskara in one part of his text, and I have to say something about, just to explain exactly the nature of these assertions. Sanskrit mathematical treatises are written with sutras that are often versified and aphoristic, and so they're written to come with a commentary. And Bhaskara himself wrote a prose commentary on his own treatises. And so these are notations from his prose commentary. And so anyway, there's two notations in the whole of the algebra. And Colebrook takes them out and he generalizes not only to all of Bhaskara's text, but to the whole of Hindu mathematicians. So we can understand what Colebrooke is doing here. He's not trying actually to make an identity of all Hindu mathematicians. Colebrooke's aim when he's doing this is that he wants to make comparisons. He wants to be able to compare what authors that were writing in Sanskrit were doing with authors that were writing in Arabic and Latin. So for him, it's in this process that he creates this. But he is creating a homogeneous idea of Hindu mathematicians and a homogeneous idea of proof along the way. And Colebrooke's publication was very influential in Europe and in Asia during all the 19th century. Mathematicians in France, like Schall and Germany, read the proofs his translation contained. Discussions on notions of proof in mathematical education were thus developed using Colebrooke's translation, and notably Hermann Henkel, for instance, developed the idea that an ideal education should combine together two types of proofs, the analytical, which was attributed to the Greeks, and the intuitive, attributed to the Indians. And something else happened was that, as you can see here, Colebrooke took proofs he found in all sorts of different commentaries and added them as footnotes to his translation, giving the feeling that proofs only belonged to commentaries and could only be so yeah, there's two things. First of all, the only proofs we see in the text he gives are in commentaries. And second, he's giving different. He's not translating the whole of a commentary, but giving parts that he considers interesting. And so visually in the text, we can see that they're made of bits and pieces. And by the beginning of this gave the idea, and this is something that it became very standard, that people say in Sanskrit, and actually they don't usually say in Sanskrit mathematical texts, but in Sanskrit mathematical texts, treatises have no proofs, they're just a set of rules, and if there are some, they're in bits and pieces and commentaries. So, but by the beginning of the 20th century, the existence of such proofs seems to have been forgotten, and standard histories overlooked them altogether. But Colebrooke's claim has been taken up at the end of the 20th and at the beginning of the 21st century by a certain number of historians of mathematics in South Asia, aiming at having the history of mathematics in Sanskrit enter a global conversation on the history of mathematical proofs. And so both the two authors I'm quoting here, M.D. Srinivas and Ramasubramaniam, both quote the quotation of Colebrooke I gave you before to say that in the Sanskrit mathematical tradition, as they say, the kind of proofs that were given were either algebraic or geometrical. And M.D. Srinivas adds also, clearly the tradition of exposition of upapatis, so upapatis, remember it's the word that was used by Bhaskara. So the exposition of upapatis is much older, and Bhaskaracharya, so Bhaskaracharya is one of the ways of calling Bhaskara II, and the later mathematicians and astronomers are merely following the traditional practice of providing detailed upapatis in their commentaries to earlier or their own works. So what he's saying here is actually that it's an immemorial tradition. It's not only in Bhaskara, it existed before, and it exists after. And then the notion of upapati is significantly different from the notion of proof as understood in the Greek as well as the modern Western traditions of mathematics. So it's really the construction of an immemorial tradition of Sanskrit proofs and opposing it to a Western, what would have been a Western tradition, as if that was homogeneous as well. And Ramasubramaniam also adds, having quoted Colebrooke, the upapatis of Indian mathematics, unlike the Western tradition, are not formulated with reference to a formal axiomatic deductive system. So he's also then opposing this tradition with the West. One often finds the statement "Iyam atravasana" when the commentator is about to begin to explain or demonstrate something. Meaning-wise, this statement "Iyam atravasana" is equivalent to "atra upapati." Both the forms being equivalent, there is hardly any consideration for choosing one over the other. So what he is saying basically is that whatever the name, there can be different names for the reasonings that are used. They're the same. It's the same tradition of proof. Okay. So behind what looks like a true interest in actors' categories lies what is in today's India truly a very strong claim, that all Sanskrit mathematical texts written over several centuries in very different contexts all functioned in the same way. And here then a mode of reasoning is harnessed to a language, if it is not to the geographical space of South Asia, to a religion, Hinduism, or to a caste, Brahmanism. Such claims then, I think you can see, resonate with what is a wider political use of history of science by the current nationalist Hindu government in India. It constructs a non-Western but homogeneous mathematical identity for Hindus. So I'd like to argue that Sanskrit mathematical texts had very diverse ways of reasoning that do not always correspond to such a portrait of the mathematical proofs they contain. And actually, they're more surprising than that. So I would like to show, notably, that proofs need not be algebraic or geometric in Sanskrit texts, and that they don't necessarily belong to commentaries, and that some reasonings might be larger or different than proofs in as much as they might not be aiming at establishing correctness or truth. So I'm going to just go through a certain number of examples. And the first one I wanted to give to you is an example taken from a treatise that was written in the 7th century by Brahmagupta, and who wrote a treatise called The Corrected Astronomical Treatise of Brahma. And in this treatise, in the chapter 2, Brahmagupta provides a table of signs with 24 values. And in chapter 21, he provides mathematical procedures that derive this table, and others, actually. So, actually, the earliest sign tables in Sanskrit sources date from the 5th century. And for Brahmagupta, the sign was both a geometrical and, for most of the authors, astronomical and mathematical authors who worked in Sanskrit with the signs, they considered it both as something numerical and geometrical at the same time. And the sign was defined actually in a figure that's called the bow field. And so it was defined from the idea of the chord of an arc, and you would take half the chord of half the arc, and that would be what is the sign. And this enabled astronomers and mathematicians to construct some of the first trigonometrical circles, and with which you could use very easily the Pythagorean theorem to derive geometrically and numerically half chords, which were the signs. Okay. So this is to say, I'm making this point just because I want to tell you that in what follows, the reasoning of that Brahmagupta is going to follow is both numerical and geometrical, and I don't know, I wouldn't know how to make a difference in it, but I don't think it's algebraical either. So what happens is that, so Brahmagupta gives 24 values of signs. And when he comes back in chapter 21 to this table, he gives rules that he gives a first set of rules which provides modes to compute 3 initial signs, which correspond to the sign of 30 degrees, 45 degrees, and 60 degrees, once you know the radius of your circle. And then from these rules, from these three signs, then he provides a rule to derive all other signs. Okay, so this is already, in doing this, Brahmagupta is doing something. So I don't know what it is. Is he showing, so he's showing how he derives his table, but he's doing something more, because actually his rules are general. They're for any radius of a circle. So he's giving rules on how to derive 24 signs, and in particular his own sign table. But he's doing something more, and which is that he doesn't give one way to compute the sine of 30 degrees, 45 degrees, and 60 degrees. He gives two ways. And it's the same thing. If you consider the rules to compute all the other signs from this, he doesn't give one rule, he gives two rules to do this. So, what is he doing? So here we have, this is typical the kind of problems we have. He's not telling us what he's doing, and even his commentator is not commenting on that. He comments on something else, and he's giving his own take on all of this, but he's not reflecting on what Brahmagupta is doing. So there's different ways that we can approach the fact that he's doubling things. Of course, you can say, well, he's giving two rules because, well, if one is not easy for you, you can use the other. If you're really making practical computations, maybe it's better to have one rule and another. But as you agree with me, there's something theoretical in the rules he's giving, because he is establishing his several rules. And another thing that we can wonder is does he think that one of the rules actually explains the other? That one is the more sort of an explanation of the other? Or is it that he believes that by giving two independent rules, he's actually showing something? So this we don't know. But actually, we have other. So the fact of doubling rules is something that we find very often in Sanskrit astronomical treatises. But we also find this kind of mode of reasoning using two rules to read one rule and then doubling it up with another rule. In a contemporary of Brahmagupta, but who is a commentator and who thus writes in prose, and who's called Bhaskara. So this is Bhaskara 1. It's the Bhaskara of the 7th century, not like the 12th century one we talked about before. And Bhaskara, in a commentary he makes to a 5th century treatise, it comments on a rule that is given by Aryabhata, and which concerns a gnomon. So we have a gnomon and a source of light, and we know this distance, and this distance and this distance, and we want to compute the shadow. We want to know the shadow of the gnomon, and. So Aryabhata gives a rule that I'm not going to read out, but basically the rule is a multiplication followed by a division. And what Bhaskara is going to say is, well, this rule actually is a rule of three. So the rule of three was the way that Sanskrit authors would talk about equal proportions or to talk about similar triangles. But what I want to underline here is that to say this, to show that he's using one procedure, he's going to reinterpret it as another procedure. Bhaskara does something specific. He turns it into a question. So this computation is a rule of three. How, if from the top of the base, which is greater than the gnomon, the size of the space between the gnomon and the base, which is a shadow, is obtained, then what is obtained with the gnomon? The shadow is obtained. So the only thing I want to underline is that there's a way of doing this, which is by asking a question. But what's interesting for me here is also that he's rereading the rule with another rule. And he could do this also, I mean, in another part of his of his commentary, he's going to also talk about the Pythagorean theorem. And to do that, there's another way. So you can take any rule where there's squares that are added or subtracted and that give another square. And to show that the rule is about the Pythagorean theorem, you're going to show that it's dealing with a right triangle. And this is done by actually renaming segments. So the segments of a right triangle in Sanskrit are called, so there's the hypotenuse is called karna, and the upright side is called koti. And so when you see a koti or a bhuja or a karna appear in the text, then it's a way for the commentator to say, you can apply, or you can reread this set of arbitrary rules as being something dealing with the Pythagorean theorem. So here, once again, we have a reasoning that has no name, but where what Bhaskara is doing is that he's taking what looks like procedures, because I forgot to tell you that, it's so obvious for me that the sutras of mathematical text more often than not are just giving procedures of mathematical problems, and general procedures that what looks like an arbitrary set of steps. When Bhaskara interprets them, they become a set of steps which step by step have a meaning, have a mathematical meaning, so that the rereading with another rule seems to be a way of giving an interpretation or explaining the steps one by one. But okay. But actually, in Bhaskara's commentary, there are many discussions about many different reasonings. So there's reasonings he does to which he gives no names, and then there's all sorts of references to all sorts of reasonings, sometimes that he names and does. So among them, he does use the term upapatti that we saw before, but it's used to be contrasted with tradition, agama. And he uses it to say, you can't take something just as a tradition. You have to give a proof for it. But he uses also other terms, like he actually gives examples of verifications, which is if you have a procedure and if you turn it upside down and you do if you invert it, would be what he calls a verification. Then there are moments in the text where he talks about explaining. And when he does this, he uses, once again, all sorts of vocabulary. So some that seem to, that could be that of the function of any commentary to explain, and other which might mean to establish, and other which might mean to show or to teach. So there's this whole variety of words, and well, we still have to understand what it means. But in particular, he uses. I'll come back. Actually, there's a slide that I probably changed place, but I'll come back to some of Bhaskara's modes of explanation on diagrams later on. So there's also another commentator I want to talk to you about, whose name is Pritudaka. And so Pritudaka is making a commentary on Brahmagupta that we saw, and Pritudaka has read Aryabhata and Bhaskara's commentaries, and he quotes them. Okay, so I'm telling you all of this because I want to show you. So we saw a mode of reasoning with Brahmagupta, then we saw a contemporary of Brahmagupta, Bhaskara, who has another sort of other ways of reasoning, maybe, or something similar. And then we have somebody who's from the 9th century and who knows all of these guys. And he's going to do other sorts of reasonings again. Pritudaka writes, the name of his commentary is called Commentary with Explanation. And the idea is, what is for Pritudaka vasana? So Actually, I'm still trying to figure out what is a vasana. I'm currently editing Pritudaka's commentary, so I'm still trying to figure out what is a vasana for Pritudaka. But there's something that he does, so I wanted to take an example of his work on arithmetical sequences. And there's, when he gives, giving an explanation, starts by sort of extending the realm in which the rule can be applied. So Brahmagupta gives a general rule for summing the terms of an arithmetical sequence. And Pritudaka first suggests to consider this as he considers a stack of bricks. Then he suggests to extend the point of view on the sequences and to consider it as a capital that's being invested once more and more. And then he considers, if you're into capital, then as something that is as a debt. So he's and so this that you're or some money that you're lending, and so you can use negative and positive numbers. And then he starts giving examples. So these are in the form of solved examples. He starts playing with the examples just with the numbers, so it becomes a numerical problem. And then he gets into another explanation, which is considering that actually. A sequence can be thought of as a sum of areas of rectangles of side one, and with each value, and that you're stacked. And along the side, he's going to say that actually then the sum of the areas of all these rectangles is equal to the area of a rectangle. So he's saying this by saying, for him, this moment, which we'd say it's a kind of proof. He would be proving that the area of this rectangle is equal to the sum of this. But for him, it seems that the explanation has to do with adding more and more different contexts in which the rules make sense. Each step of the rules makes sense. And actually, he goes on in his commentary looking at, he gives a rule to sum the terms of a geometric sequence, and he explains it by understanding this rule as being part of a discipline that's combinatorics, but that is used in versification in Sanskrit. So in Brahmagupta's astronomical treatise, there's a whole chapter on these combinatorics of versification, and Pritudaka is going to explain the geometrical sequence with this. And he's going to also use algebra, and in another rule he's going to interpret these geometrical sequences as being linked to algebra, or being that you can understand them in algebra. So in other words, I'm not sure yet what is an explanation for Pritudaka. For him is something that's so important that he's giving the title to his commentary about this. But it seems that what he's interested in is looking, if you take a procedure, at looking at all the different contexts in which it can be more than applied, in which it has a meaning, and that these contexts need not be mathematical. They can be because for Brahmagupta, actually, algebra is not part of mathematics. It's part of astronomy, for instance. Okay, so this was an example. So there was a whole tradition of, so this is where I get back to my diagrams. There was a whole tradition of explanation on diagrams that we find in Sanskrit mathematical commentaries. And the problem with these explanations is that a lot of them were oral, so very typically, Bhaskara, the one who comments on Aryabhata, will say, when he says, okay, an explanation should be given on a diagram, and then the diagram is drawn, or sometimes it's not even drawn, and you're supposed to see from the diagram what are the rules that are given. And actually, I think that the diagrams themselves, we see them circulating from text to text and commentary to commentary, even though, as you see from commentary to commentary, the way of explaining, the values given to how you explain change all the time. But it seems that, that these diagrams were also a way of a repository of giving proofs and committing them to memory. I see them as small libraries of proofs as they circulate. So this is the famous trigonometrical circle, and this one is actually a diagram that has to do with cyclic quadrilaterals, which was one topic on which Brahmagupta reasoned a lot, and that interested so much German mathematicians at the end of the 19th century. And Prithu gave a diagram of one of these cyclic quadrilaterals, and even though it might not look like one, it looks like a triangle here. But and that circulated very much. Okay, so I want to end maybe of all my examples of all these different types of modes of reasoning that for our authors were seen as validating what they were doing. To talk about another commentator, Shankaravariyar, who was from Kerala, and from the Kerala school. So in the Kerala, from the 15th century onwards, there were a certain number of mathematicians based in the southwest of India, really developed some incredible mathematical procedures, notably to approximate pi and the signs with what looks like something like infinite series, and so they're held sometimes as being the prehistorians of calculus. Some people even think that Jesuits could have stolen some of the text and transmitted it to Newton secretly or something. And indeed, actually, in the 15th, what happens is that a lot of these rules are attributed to Madhava from the 15th century, but we only have them through quotations of commentators and treatise writers who are going to write on them. So, and in one of his commentary to the Lilavati of Bhaskara, Shankaravariyar comes up with. I don't know if I have comes up with a proof for this approximation of the circumference of a circle, which is another way of giving an approximation of pi. And Shankaravariyar actually doesn't talk about upapati or vasana. He really is talking about establishing the truth. He's using sad and he's using expressions about this. And something else is going on is that when he uses the rule of three, when he wants to show that things are proportionate, well, sometimes he uses the question mode, but sometimes he uses, reasonings about the nature of the things that are compared that really makes us think of the kind of reasonings that were done in Euclidean geometry. So, although this needs to be more elaborated, it seems to me that we have here somebody who is writing in Sanskrit, but seems to be doing something that is a hybrid, probably of a Sanskrit tradition, but of a Euclidean standard proof of some sort. And so, these modes of reasoning traveled also and hybrided themselves. Okay, and so to come to my conclusion, there is something a bit arresting in the persistence of this ignorance on traditions of proof outside of the Euclidean norm, which has to do maybe in part with what the philosopher Achille Mbembe calls late Europeocentrism. that is, of the persistence of Eurocentric and colonial structures of thought in a world where everybody knows that Europe and the United States has never been the unique place in which worthy intellectual productions were composed. So I have entitled this presentation, Let's Decolonize the History of Mathematical Proofs, because I believe that decolonizing the history is possible only through a collective critical effort, that as professional historians of mathematics, but also as teachers, as an educated public, such as the one in Gresham, we should not let's spread a discourse which closes the doors of what mathematics is or not. So mathematical reasonings were and still are very diverse. They are not necessarily about truth. They were certainly not homogeneous across a geographical area in the same language or by people who had the same religion. So let us remember this when we hear people speaking of Western science, British mathematics, or Islamic proofs. The good news is that we have resources to write other new histories that are more stimulating, histories that testify to how, just like today, people practicing mathematics had many different ways of reasoning, and that there were whole ecologies of argumentation that still need to be investigated. And I don't think that these modes of reasoning necessarily will give anything to mathematicians today. I don't think they're going to bring new mathematical ways of reasoning, but I think that they're a testimony of a part of our common humanity in its culture, like its cultures of reasoning, in the same way that we're interested in beautiful pieces of art or beautiful pieces of literature wherever they come from and whatever their time. So there's beautiful pieces of reasoning, and they're interested just like that and in themselves. Thank you.
So you gave an example through sign values about using two different methods, two different ways to find the same answer. And instead of just using one way to find one answer, he went and interpreted it in a different way. Do you think that finding two ways to find the same answer is important, and why?
So actually, as a historian, I'm not going to make any statements about if it's important or if it's good or if it's the truth. I'm interested in describing how it is, but I find it interesting. And actually, one of my points that maybe wasn't clear because I'm still trying to find for myself how to interpret the fact that many authors in Sanskrit wrote two different rules, what could appear as two different rules for a different... Why did they do it? What was behind it? And actually, I think there were different interpretations. Sometimes they really thought that there were some fundamental algorithms, like the rule of three, like the Pythagorean theorem that was thought of as a procedure, and that these were like the basis from which all the other algorithms could be understood and get a mathematical meaning. But sometimes maybe it was really thought that if you arrive at the same place from two different ways, then you're gathering a sort of strength and proving something that's correct. But we need to know what the idea is, to understand what the actors themselves, the authors themselves thought. So we're lucky when they really tell us, but if not, we have to use all sorts of clues to try to guess.
I'm not really sure if this makes sense, but would you say that the rules and findings made by Hindu, Chinese, or Arab mathematicians, which may be different to findings by Western mathematicians but still accurate, could be more relevant today or even taught at schools than the findings made by Western mathematicians if reoccurring Western dominance wasn't to exist?
First of all, I want to just say that I don't understand, I honestly don't understand why we just don't integrate, different mathematical texts in the histories we write. So it could be in the kind of histories that the preliminary stories that we give in math textbooks, or just in the general public. So there's something which is what I call actually Achille Mbembe calls the persistence of ignorance. So it's really this, and which I think has to come with, in a way, to be more direct. It's the legacy we have of racist and white supremacist modes of thought that come from us from the 19th century or the late 19th century, and that is our legacy. And what I want to say is, okay, then after that, mathematics is part of our humanity. As soon as we have writing, we have mathematics. And as soon as we have mathematical writings, we have things like the Pythagorean theorem. So it's called the Pythagorean theorem, but actually it's something that's common to us as human beings, I'd say. But of course, there's different people who did different things at different times. But one thing I want to say is not like, even if you were a Hindu, so first of all, you could write in Sanskrit and not be a Hindu. But even if you were a Hindu writing in Sanskrit in the 7th century, you could be doing even if you were neighbors, you could be doing two different things. So that it doesn't make sense to say that, to make a huge bag and say, oh, they had the same religion, they had the same language, and of course, yes, they did incredible things. They did incredible things sometimes before Europeans did something that was similar. But that's not my point. Is we're not in a race of trying to show who was the first. I think it's also interesting in itself and in understanding how a 7th century Sanskrit commentator thought about mathematics and what he thought a reasoning that was interesting was. And maybe it wasn't about truth. Maybe it was about something else.
So I was wondering if in these various texts of mathematics in India, if there is a different conceptualization between the different parts of mathematics, between algebra, between geometry, arithmetic. Is there a different idea of the relation between them as opposed to the Greek legacy of mathematics?
Okay, thank you for this nice question. Actually, so there's, of course, what each and every author thought about mathematics is still something we need. I mean, we're still editing these texts and trying to understand them. But certainly, authors, first of all, distinguished in between different topics of mathematics. So they did have they did talk about arithmetics, geometry, and algebra. And Bhaskara too, Bhaskara Acharya is very famous because he's the one, he actually saw a continuity in between arithmetics and algebra. So for him, there's something about, I don't think it's the quantities, it's the operons, it's the kind of things that you can operate on. So there would be something like a common structure. And so Colebrooke, who knew a little bit the algebraists in England at the time, forced a little bit Bhaskara's, in his translation of Bhaskara's algebra and arithmetic, the structural link that would make that algebra would be sort of like a fundamental structure that could explain also arithmetic. But there are elements of this in Bhaskara's text. And okay, so and if you take so that's Bhaskara, the canonical Bhaskara of the 12th century. The 1st century Bhaskara has is different in his conception of mathematics, in the sense where he gives several definitions of how you can think of mathematics, and he doesn't decide which one he wants. One of his definitions of mathematics is to say, actually, mathematics is the science of algorithms, of computing. And so they could be, then you can distinguish the different types of objects that go in it. So it can be arithmetical objects or geometrical objects, but what counts is the algorithm. But then he says, then you can always give a geometrical interpretation to an arithmetical problem and vice versa. And but he never goes back to this, so it's just like a statement that's there. And in his commentary, algebra is not so important.
One example of where East meets West in mathematics, I think, is Ramanujan. the Indian mathematician who was working with Hardy about 100 years ago. And my understanding of the situation there is that Hardy's initial reaction was that Ramanujan had no idea of proof whatsoever, and but nonetheless he respected his great mathematical intuition, and it's subsequently been found, as I understand it, that many of Ramanujan's statements were actually true. Some were false, and some, I think, are still unproven. Do you have any comments on that? Was Ramanujan influenced by the Indian traditions of mathematics?
Well, of course, I don't know. I haven't worked on Ramanujan's work, and I wouldn't dare to say so. But wouldn't it be just natural that he had some? I don't even know his biography exactly. He probably, at the end of the 19th century, he probably was trained in a kind of curriculum that was available for Indian students, so that would have been in English mathematical manuals, but he could have also had access to other South Indian traditions where he was. But I just wanted to underline that East meets West is all along the history of the South Asia. And so, like for instance, in Kerala, it seems to me that when we see these proofs coming up with these rules of proportion that are completely different, it gives the feeling that there was some kind of knowledge of other types of mathematical and astronomical traditions that were there, and they probably came from. Well, it was during the Mughal Empire, so there was a lot of Persian texts going on. But even before that, in the 5th century, actually, some of the first astrological and astronomical texts that we have in Sanskrit bear a Hellenistic influence. So on the one hand, I think that in India all the time there was always all sorts of text modes of doing mathematics and thinking about it that came in and were absorbed into all sorts of different ways of doing, and reciprocally, as you know, it's like the idea of trigonometry or part of the arithmetic that was developed in South Asia also traveled. So I think this is my point, is does East and West really have a meaning? Isn't it something that we constructed, and that if we hold on to it, we're creating a divided world by holding down to these categories. So.
Okay, thanks. So I'm afraid we do have to stop promptly, but I just want to flag up, if you have enjoyed today, the next sort of mathematical lecture at Gresham will be by the Gresham Press of Geometry on the 22nd of November, so you can look on the Gresham website for that. The next BSHM meeting will be our Christmas meeting on the 3rd of December. Check out our website for that. I just want to thank everybody who's been involved in organising this event today. And finally, of course, let's have a gigantic round of applause for our speakers. Thank you.